Again, I'm sorry. I just made a quick introduction and gave them an instruction to come up and ask questions if they have any. So go ahead. I didn't realize I was muted. Sorry.
All right. Okay, so hello everyone. I hope you're all having a great time meeting in person today. So I wish I could be there in person as well, but unfortunately, glad to participate at least remotely today. So first of all, I want to thank Professor Regina Lee and the TEPS committee for inviting me to talk about my research work here today. And also, I think the Ontario Science Centre is a fantastic venue, and I hope you're really enjoying that as well. This reminds me of a small personal anecdote. When I was a teenager and visiting the GTA for the first time, I remember 3 highlights from that trip: the CN Tower, Niagara Falls, and the Ontario Science Centre. So over the decades, I've had great times visiting it with my family and friends. So you have a really amazing asset in the GTA, so hope you will take the time to enjoy that besides the conference also. Okay, so moving on, what I wanted to do is talk to you today about multispectral imagers and integrated photonics for remote sensing and space exploration. So I will provide a very brief overview of research activities in my group in this area. And if you have any sort of detailed questions, happy to take it at the end of the talk or afterwards by email. I know this is a little different from the exoplanetary science, but what is common here is the core instrumentation technology, which can be adapted for both astronomy, as well as what I will be focusing on is looking at sort of Earth observations, remote sensing, and planetary surface rover missions. Right. So as you're all probably aware, photonic technologies has broad applications in remote sensing. So I show here a select few of them, particularly in the areas of agriculture and climate change, which is becoming very important today. And you have over here Earth observation satellites in the area for climate change, low-flying planes, which are using imaging technologies. And for those of you interested, the Optics and Photonics news magazine in November 2019 gave a great overview of photonics used for tracking global climate change, right? So at Western here, we are looking, also working with Nunavut Arctic College, located in Northern Canada, where the Arctic sea ice changes are important. And so they're very interested in looking at Earth observation to track them, which is also key. And finally, the main topic area, sort of which, where most of my applications are focused towards, is precision agriculture. This is being increasingly automated using remote sensing imaging and in-situ sensor suits. So over top here, you see it in terms of for drones and tractors, which have sensors. And also more and more, we're seeing satellite imagery also being used for this. So imaging is a very key technology over here. So particularly, I'm going to be talking about this multispectral imaging. So what is multispectral imaging for those of you who may not be familiar with it? So everybody knows you take images like on any camera, like on your smartphone. And typically these images that you take are what we call RGB images. So red, green, blue, like the image over here. And what you see is these kinds of images give you 2D spatial information. But what we also want to capture is a rich spectral information from light reflection off of different surfaces. And that is something we want to capture. And how do we do that? There are 2 main techniques in this field. One is called a hyperspectral imaging. Another one is called multispectral imaging. They're very related to each other. Hyperspectral imaging just takes a large number of spectral bands. So you get very close spectral information, almost a very continuous curve. So if you take this image over here, you get this 3rd dimension where you get the spectral image for every point on the image, right? Multispectral imaging is just very similar, but you take it at fewer slices and sections. And then what we do here is then look at any point. And what we're interested in not necessarily is a spectral curve, but just some key spectral information from which we can obtain what's known as a spectral signature. So this kind of multispectral images give us a spectral signature on top of just the morphology or the 2D image you regularly see. So why would we like it? Why do we want this? It helps us characterize the object, and we can analyze this kind of data using deterministic functions, or more and more what we're seeing is machine learning algorithms. So this multispectral imaging as a technique has many applications, from food quality, from geology and agriculture, just to name a very few of them. Okay. So in precision agriculture, remote sensing is very important, particularly in our region here. We're in Ontario, and where I'm standing in southwestern Ontario is full of fields. And so it's very important to monitor crop health and resource management. And so what you see on the top here is an RGB image of a diseased leaf, but you don't really see much of that information. But when you take it in sort of this is a processed multispectral imaging called an NDVI, then you can see which parts of the sections are healthy, which parts are diseased, and so on, right? So similarly, this is at the plant level. This one is at the sort of farm level. And so we can give some information to farmers just from these kind of remote sensing multispectral imaging. So what we are doing in my research group at Western is we've collaborated with a local industry partner in our Canada labs. And what we've done is build a very customized modular multispectral camera. So this is a key for future applications for where it is very customized for the region and the type of information we're looking at. And what we're really looking at is hitting high spectral accuracy, but small enough so that we can put it on things like the UAV. We're also looking into future for looking and putting it on satellites for satellite imaging as well, but also for greenhouses. And for that, we need things like adjustable field of view. And I'll talk about this a little bit in the, towards the end. We also look at something called radiometric accuracy. So it's not important just to have the information and the image information and the spectrum. We need to figure out how does that correlate with other things that we are measuring with some level of accuracy. So this is what we're looking at. Okay. So here we see a remote sensing. Just wanted to give you an idea of what kind of image products are there, how this actually operates. So you would actually put the multispectral camera at the bottom of this drone, then fly it over a farm. And over here, what you see is what's called a stitched image of one of the bands. And then over here, what you see is then sort of the layering of the different spectral slices. And so hence this is called a multispectral cube. And so we look. Just some different information here. This is the image product that comes out of this kind of instrument. This is for farms. Over here, what we've done is also taken it for some geology, rocks that we have on campus, and we try to image them and get them at different spectral bands. So what are the key performance measures that we want to see? We want to keep resolution of the image as high as possible, and also get a precise spatial and spectral data. So this is where I'll go back to, remember we talked about hyperspectral imaging and multispectral. So typically this is a trade-off. So you have to trade off the resolution of the image versus the number of spectral bands that you want. And so therefore, multispectral has some niche applications, hyperspectral also has some niche applications. Wide area coverage, spectral range, and cost and weight. So when we're looking for applications such as the drone, for satellites, microsatellites, and rovers, this cost and weight also becomes very important. So this is really a trade-off of making sure we get the balance of everything for a particular application, which is quite challenging. And just some results, some very preliminary results from the kind of cameras that we built. So this is a leading commercial camera, and this is our camera over here. What you see here is sort of the actual spectral response, but then the points over here are the spectral data from the multispectral imager at a particular point. And what we see is ours tracks very well with what we want to see from a particular reflectance, whereas some of the leading commercial kind of miss some of these points, right? Of course, everybody's getting better. This is a very dynamic field. Every day people are improving. So this is the data we had taken a little while back. Just another way to view the images so you can see what we're doing with, this is just the same multispectral imaging. This is RGB, this is the spectral imaging that we take out. What we're also doing, and I'll talk about this in the context of the lunar rover, it's interesting that with one sensor, you can look at wavelength ranges from 400 to 400 to 1 micron. But what is very interesting is there are some interesting spectral bands that we want to see from the 1 to 2 micron and beyond. So some of the other work that we're also looking at is to extend this 400 to 1700 so that we get a WIS, NIR, and shortwave IR multispectral imager. And so that's what we're looking at. Okay, so I wanted to mention one key point because you're looking at these multispectral imagers. That's great, we take the images, how good are they? So one key aspect for all these, this kind of imaging is we need to do radiometric calibration. So if the images are not calibrated, then they have very little use in terms of their spectral information. So one of the key steps here, if you can see here, we have some kind of reflectance. We are then capturing that reflectance, whichever technique you use. So what we need to do is calibrate this, and usually there's some kind of calibration. How you operate these instruments is usually you have a calibration panel that just before you start your flight or something, you calibrate it to those conditions for the day, fly it, and then apply that to the images that you receive. One of the issues with this kind of calibration, which is typically what's done, is that you get a one-point calibration. If the conditions change, if the lighting conditions change, then that is not captured. So something like Ontario, we get cloud coverage all the time. So if you are having an instrument that's tracking a field, but you have clouds in between, this changes the light conditions. So this changes some of the spectral information. So one of the things that we have done, another improvement that we've brought in for this particular application is to include photosensors, not only looking down, but also looking up. And we have done some work, very preliminary work in actually trying to take the sensor data from both of these photosensors and give what's known as in situ real-time calibration. So this is very key for this kind of application. And so that's something we are doing. But I don't have time today to actually go into full details of what we do with that data. But that's something we have looked at. Okay, moving on, what other applications are there? The same multispectral imager, we have put that on a mobile robot. So here you see we call it the greenhouse robot or the greenbot. And the greenbot here is actually in a greenhouse in southwestern Ontario. And we're taking imaging down these big rows. And you should keep in mind, these greenhouses are not small. In a lot of cases, these are actually as big as fields or even bigger. And so we've done some autonomous navigation with my colleague, Ken McIsaac in electrical engineering. And some of these robots can actually navigate autonomously and take images, multispectral images. So this is part of work we have done also with A&L. Okay. So moving on, let's switch gears a bit. So other applications, the other application that we're interested in is multispectral imagers are also key for geological classification. So over here, as you are all probably aware and have followed the Perseverance rover that landed on Mars, and it has 2 multispectral cameras, and it has about 12 bands in total, among many other instruments that it is carrying. So it's also looking at multispectral information. In our group here, we're interested in upcoming lunar missions. You all know there's a lot of imaging that we want to do on the moon. Why and how are we going to do it? There are several missions that are planned, both manned and unmanned. And what are we looking for on the moon? So keep in mind, when we talk about multispectral imaging, we need to know what the application is to customize it. So one of the things we're doing is to evaluate the in situ resource utilization potential of something known as the permanently shadowed regions of the lunar poles. Particularly there, we're interested in looking at water ice. We're also interested in characterizing the composition of rocks and regoliths, within this permanently shadowed regions or the PSRs. And I'm not a geologist myself. I work with geologists at Western. This is with Dr. Osinski's group. And so they want to look at olivine, pyroxene, plagioclase, spinels, and lunar glasses in these areas. So what we are trying to do is build instrumentation that includes cameras to image and use them for these kinds of classifications on the moon. And so we are actually, I'll show several versions of the multispectral images that we are developing for particularly rover instrumentation on the rover information. Now, lots of information is already known from previous missions, and we will get more from the current and upcoming missions. However, there is still a lot that we do not know. So really, there's a lot to discover over here. A little more about these permanently shadowed regions of the moon. A couple of things to keep in mind. And I'll talk about this in one version of the instrument. If you're particularly targeting this region of the moon, it's not just a very cold place, it also gets no sunlight. And of course, that's what makes it interesting, because we can potentially find water ice there and other volatile compounds, which have been identified from orbit to be there. And over here, this is just an example of what we think the distribution of the lunar ice is as detected by NASA's M3 instrument. And many fundamental aspects of the lunar PSR water is not well understood. So, such as its existence, distribution, characteristics. So this is sort of a very main focus of several lunar missions going into that region. So some of the missions that are upcoming, as you know, probably know, the Viper mission is coming up. This is particularly looking at these volatiles in that region. And you also know the China's U2 rover, which is there as well. And Canada will also, as if you followed the recent announcements, is also working on a micro rover, and so are several other countries. So several commercial partners are also sending instruments. But what is exciting about this? So we have large rovers, but we are also looking at sending smaller rovers, which are slightly low-cost missions. Low-cost missions means that we have to think about low cost, low power, low weight. And from an engineering point of view, this is quite challenging to balance out the science requirements with the engineering constraints. So this is really what we're looking at. Okay, so currently we are developing under a contract with the CSA for what's known as an integrated vision system. This includes this is not for a micro rover, this is for a larger rover. So this includes a multispectral imager. I will talk a bit more about this, along with a multispectral LiDAR, which is being developed by MDA. So this is the concept of the instrument that we have so far. Where would this instrument be? This instrument would be mounted on top of the rover mast. And depending on how we tilt it, this would, we have adjustable distances. We can see different distances, different resolutions. And if you have a 360-degree rotation around the mast, so this is for sort of larger rovers, then we can do imaging of the instrument on a 360-degree angle. Okay. So let me just talk about the MSI. So my group is really involved in building this particular MSI for the integrated vision system. And it can also be a standoff instrument as well. And what it has is, what is very interesting is this has two sensors. So this is where I was talking about how we wanted to extend our capability. So it has a CMOS sensor, which will give you the range from 400 to 1000. And most of the multispectrals that you read about actually cover just this range. But what we also want to cover is the 1 to 2 micron range, particularly the 1 to 1.7 microns with this second sensor. And then add that to a filter wheel so that we can get different filters, about 10 or 12 bands. And then this here is our entire instrument over here with all the other electronics that is needed. And so this is what we're working on right now. So we're actually working on a prototype of this instrument right now, which we will hopefully field test early next year. And moving forward, that's one version of the instrument. I mentioned to you that we're looking at the PSR regions of the moon as well. And in the PSR regions, what you don't have is light. So what we can do is also integrate an active LED illumination along with this MSI. So this one is a smaller version. This would be something for a micro rover. And with an LED ring, that would work on a rover in the, that is targeted for the PSRs. And then in this case, it is not it's not a dual sensor, it's a single sensor, because otherwise it's a very large instrument, which none of the rovers can carry. So this is an AI MSI. This is also another instrument design that we are doing over here. Okay, so I'll end it there because keep in mind, you'll hear more about this as we go forward. We are aiming to build a multispectral imager developed by Western. Hopefully that will go on a lunar rover in the next few years. So that's where we're looking at. So this is very exciting for us over here. Okay, so let me shift gears a bit. Again, as I said, I was giving a brief overview. And wanted to talk about another project actually that Dr. Lee is also involved with. And this is the other aspect of it is to use photonic integrated circuits for satellite communication links. And this is a project that is led by Honeywell Aerospace, funded by CSA and MITAC, and has a large collaboration. So it's very exciting to work with this large collaboration, which includes myself and my team from Western, but Regina Lee and her team from York, Dr. Winnie from Carleton, and Dr. Amar Hamlin from Toronto. So a huge people with everyone working on different subsystems. And what are we trying to do? So over here, as you know, if you followed again the news, so many companies have now launched not just 1 or 2 satellites, but constellation of satellites for the low Earth orbit. And mainly, a lot of them, as you know, are providing broadband internet. Now, one of the requirements for this is, intercommunication between these satellites at very, very high speeds, somewhere in the order of tens to hundreds of gigabits per second. Also, these have to be low cost. When we want to deploy large number of satellites, we want any technology that's there is not just robust, but also low cost so that they are commercially viable. And what is the requirement here? We have very tight beam requirements. So if you look at this satellite to satellite communication that is needed, very tight beam requirements under under very harsh conditions of vibration and temperature. And currently, most of the beam steering between the satellites is done using a mechanical means. This is fairly large and expensive. So this optical phased array that we're working on is looking at an on-chip solution, which is an electronics beam steering. And it's also much smaller than sort of the mechanical interface that you would have. And so this is the project. This is an exciting project they're working on with different teams, working with Honeywell on the different subsystems, as I mentioned. And at Western, what we're working on, for those of you who know this area, we're working on sort of the optical antenna grading element systems and sort of what we call multi-mode interference, which will split and combine several of the lights on chip. And so these are some of the subsystems we're working on. And then actually Honeywell is integrating all of this together, and we're involved in doing the chip design, fabrication, and testing. All right, so hopefully I gave you an overview of some of the research work that we're doing at Western. Happy to answer some questions. Before I close, I just want to take a couple minutes to talk about also Western's Institute for Earth and Space Exploration, which was launched in 2019, but previously was, it was promoted from a Center for Planetary Science and Exploration, which you might be familiar with. So this institute is very interdisciplinary, has 60 faculty members from 9 faculties, 20 departments. It also hosts, for those of you who are interested, the collaborative specialization in planetary science and exploration. So lots of training opportunities and research for the next generation of our space engineers and scientists. Very quickly, I'll just say what we are trying to do is launch Western into space. So not very different. I know at York, you have this as well. So we have high altitude balloon flights, instrument development, as you've seen, small satellite and CubeSat projects. And also, as you saw, the Earth observation piece, we're getting data back down to Earth. This is also very important. So these are some of the sort of broad themes of the Institute. More specific themes, we're looking at Earth observation, exploration technologies, which some of them I covered, planetary processes, materials, galactic and stellar processes, space health, and space policy and law, which is also becoming more important with these commercial ventures. As you also know, York is Western, along with York, so Western's Nunavut Arctic College CubeSat project, UPIC-1, is one of 15 teams that is funded by the CSA to build a CubeSat that will be launched in 2023. So we're also working on one of those. And we have a payload, which is a PR imaging camera. Sorry, this is what we're looking at. Okay. And some new initiatives, we're looking at space resources, space health, Earth observation. So these are actually more areas that are being developed right now through the Institute. The collaborative specialization, for those of you interested, please look at the website. It's a very, one of the few programs looking at sort of planetary science and exploration and giving a very interdisciplinary flavor to that, involving Earth science, physics, astronomy, electrical, computer engineering, and geography. And we're actually expanding it into health and law. So a very interdisciplinary program. We have summer internships for undergraduate students, but also professional students. And we have a new professional master's program that will open up in 2023 in interdisciplinary space studies. And these are just some of the examples of some of the field work that some of the students in the program have been involved with. And this is our HAB team there. Well, and just when they with their payload. Okay. So with that, let me end. I want to acknowledge there's a huge research group that we work with, both my group and all our collaborators. And there's this work done by a fairly large group of not just university people, but also a lot of the industries. Okay. Okay. I would like to end there. Thank you very much for listening to me. And if you have any further questions, happy to take them now, or you can also see the links on the screen.
I'm not sure if you can hear me, but oh no, you're going to the unfortunate time. Any questions? Anyone? Oh, come on. Do ask away. Yes, you have to come up and ask.
I know it's after lunch, so you have to come to the front.
I was wondering, I'm not very familiar with most of what you talked about, but the spectral imager, I was wondering what's the typical spectral resolution that we have, that you have with those?
Right. So for the multispectral imagers, it is we can actually design the filter to be what we want. So those filters are usually on the order of 10 nanometers. So spectral resolution of the individual bands can be anywhere from 10 nanometers to 30 nanometers. So, yeah.
Hi, Jayshri. My question is just, you talked about putting imagers on the UAVs and other sort of drone devices. And I was curious how you're going to compensate for changes in resolution with the height of that instrument, just like with the cameras and things like that. Thanks.
That's a very good question. So the resolution is very much determined by what height you fly it at. So what the resolution is determined by the sensor's sort of intrinsic resolution, the pixel size of the camera. But then what you also have, what you can play with is the field of view. So if you want you have to have a trade-off. If you have a very large field of view, then your resolution will drop. Of course, if you go higher, also your resolution will drop. So typically when we look at for the drone applications, we know what kind of heights they will be flying at. And so based on that, we will choose what lens we want for the resolution that they want on the ground. So that's actually something that we have to adapt based on what application we're looking at. In fact, for the lunar rovers, it's actually quite critical because we have to take into account, for example, from the science side, they will say, okay, we want to be able to see 2 millimeters. So this is our resolution that we want to see spatially from a distance of about 3 meters. So then we will backtrack and see what kind of field of view we can actually use with the kind of sensor. And then this will actually determine what sensor we choose and what kind of lenses we will choose. So yeah, so that's actually quite a bit that goes into that study. So very good question.
Thanks, thank you. It was really awesome. Thank you. Hopefully next year we can do this. And so you'll be a lot of people and you'll be using your lab as well. Thank you.
Okay.
Okay, so with that, there's a couple of quick rules about preempting. You will be called and you'll be using microphone. I'm going to set up microphone.